Hello all, my name is Ashutosh Rastogi. I'm a teacher by profession. My mission is to impart quality education for all. For that purpose, I am creating these videos. If you appreciate my work, then please do like my video and subscribe my channel so that I could get the motivation to prepare more videos. Anyways, today in this particular lecture, we will going to study this Super Heterodyne receiver in your AM application. So these are the outlines. We're going to start up with the introduction where we have discussed that whatever we have learned in our earlier lecture. Then we're going to discuss some of the important effects such as your heterodyning process and image frequency. Then we're going to discuss the block diagram structure of your super heterodyne receiver. Then we will going to discuss image frequency rejection, how we will going to do that, and the frequency mixing operation where we will going to learn various frequency modification operation with the help of example. And finally we are going to give a comparative study about your TRF receiver as well as your heterodyne receiver as per their working principle. So in our previous lectures we have discussed about your receivers and their desirable characteristics such as its sensitivity, selectivity, fidelity, etc. So what a typical receiver is, it can receive analog electromagnetic signals or wave, or you could say a digital signal through even your wired or wireless medium, and it has to convert it into the original form. This is your typical receiver's functionality that any receiver must have to do. So in our last lecture we have discussed about your tuned radio frequency receiver. We have also discussed about its various advantages as well as disadvantages. In terms of advantages, we have discussed that it is very cheap and easier to construct, whereas as your disadvantages we have seen that at higher frequencies we will be having much deteriorated outcome, just as high quality factor filter are not easy to construct. So now in this particular lecture we are going to discuss about very popular receiver, that is your super heterodyne receiver. So super heterodyne receiver was invented by your Armstrong in your 1918. Super heterodyne receiver would have been used in your AM, FM or your TV broadcasting, cellular, satellite systems, radars, GPS. These are name a few of different sorts of application where super heterodyne receiver might have been used. So before we will going to discuss the super heterodyne receiver into our greater detail, let us discuss some of the important effects in your super heterodyne receiver, that is heterodyning, what it is, and your image frequency, what image frequency is. So this particular figure is basically showing your heterodyning concept. So heterodyning is nothing but it is same as your frequency translation or a frequency conversion. So in the front end of our super heterodyne receiver we will be having an antenna which will going to receive all the incoming frequencies, and we had already studied that RF signal strength is very low, so we have to select a specific frequency band and then we have to further amplify it out. So heterodyning is nothing but it is your up conversion or your down conversion operation. That is, while receiving our signal we will going to translate onto another frequency signal which is your fixed intermediate frequency. About your intermediate frequency we had already discussed when we have studied about your TRF receiver, where we have discussed various intermediate frequencies for different sorts of application. So here the idea in super heterodyne receiver is to down convert our incoming RF signal to some lower frequency or intermediate frequency, then we have to perform subsequent processing. So this is the key idea in your heterodyne receiver. So now next one is your image frequency. So image frequency is equivalent to the second radio frequency that will produce an intermediate frequency that will interfere with the IF from the desired radio frequency. So the point is, image frequency is another frequency which will going to produce the same impact as your desirable message signal. So it will basically going to produce certain sort of interference which will going to impact or affect the signal quality. So it is basically your undesirable effect, and anyhow we must have to avoid it, this image frequency. So if the selected RF carrier signal and its image frequency enters a receiver at the same time, they both will going to mix up with the local oscillator frequency and they will produce different frequencies that are equal to your intermediate frequency. So obviously if this will going to happen, it will further going to enhance or increase the interference which will going to distort our received signal quality. So image frequency is given by your signal frequency plus twice the intermediate frequency, that will be equal to, image frequency will be equal to FC plus twice of IF, where FC is the carrier frequency and IF is the intermediate frequency. So image frequency will going to basically occur at this particular frequency ranges, that is your FC plus twice of IF, and it is an undesirable effect and we have to avoid it. So higher the intermediate frequency, the farther away the image frequency is from the desired radio frequency. That we have already seen that F image will be equal to F of C plus twice of IF. So if IF will going to increase, the image frequency will also going to get farther away. So therefore, for better image frequency rejection, a high intermediate frequency is preferred. However, the higher the intermediate frequency, it is more difficult to build a stable amplifier with the high gain, as we have seen in your TRF receiver functionality also. So at higher frequency, our amplifier will not going to produce uniform gain, which will further going to distort our signal. So therefore, we need to perform a trade-off when selecting the intermediate frequency for a radio receiver. Although there are certain standards for different sorts of applications, we will be having different intermediate frequencies. For AM application, we will be having this intermediate frequency value will be equal to 455 kilohertz. So image frequency rejection versus IF frequency gain and stability. So this is our trade-off points where we have to perform this trade-off. That is, if we will going to increase that particular frequency of operation, then it will going to make image frequency farther away from the message signal, but side by side it will also going to affect the intermediate frequency gain and the stability. So we must have to make a trade-off between these two things. So this particular figure is basically showing the block diagram structure of your super heterodyne receiver. Initially we will be having this antenna, which will going to convert our incoming EM radio wave signals into your electrical counterpart that would have been centered around your desirable frequency ranges or carrier frequency, you could say. So this RF section will going to provide this amplification over the selected frequency range signal. Then that signal would have been passed through your mixer, which will going to perform this mixing operation. Both these mixer and RF section will going to have this input local carrier oscillator frequency, which would have been given as your FLO will be equal to FC plus F of IF, where this FC is the central carrier frequency and FIF is your standard intermediate frequency. So both these blocks, that is your RF section as well as your mixer, they are being ganged up, or you could say they are fully synchronized. That is, they will going to operate over the same frequency ranges. So what mixer will going to do is it will going to produce several frequency components. So let us understand the operation of mixer. Let us say that mixer is having these two input frequency components, that is your F1 and F2. Then what will the outcome of that particular mixer? So it will basically going to generate four frequency outcome. That is, one is your summation, that is your F1 plus F2. Second one is your F1 minus F2, F1 as well as F2. Whereas in general we have seen that your product multiplier will going to generate two frequency component, that is F1 plus F2 and F1 minus F2. So mixer is different in that particular aspect. It will basically going to generate all four frequency component or the combination of all the frequency component. So then that mixer outcome will going to pass through your intermediate frequency amplifier, which is basically being tuned to select only those components which are centered around your intermediate frequency. Then we will going to amplify them out, and after that amplification, that signal will going to pass through your detector depending upon what type of application we are using. Since we are using this AM application, so that detector circuitry could be any of your AM detectors such as your envelope detector or diode detector. Whereas if our application is different, then depending upon that application we can use a specific detector circuitry, and side by side in that particular case our intermediate frequency value will also get changed. Here one important block is also there, that is your automatic gain control. So what is the responsibility of this your automatic gain control is it will basically going to gives us the optimum outcome or optimum output of the signal value irrespective of the signal variation. So this will basically gives us the better quality reception without fluctuation in your received signal quality. After detector we will be having this your baseband output or voice signal. Obviously your detector output further pass through your amplifier, and that would have been connected to your end device such as your speaker. So this is the overall block structure of your super heterodyne receiver. Now let us understand it into the greater detail. So RF amplifier basically will going to amplify the weak RF incoming signal out of the antenna, which will being tuned by the tank circuitry to a specific carrier frequency, and it will further going to reject the image frequency. So here high selectivity of that particular receiver will going to comes into picture. That is, amplifier will going to only amplify those frequency components which are lying into the bandwidth of that amplifier. So for high amplification, class C amplifier would have been used in your RF amplifier. So bandwidth of the RF amplifier is much wider than the signal bandwidth, so that we can contain much larger amount of information. Then second block is the mixer. It will going to perform the frequency translation as we have already discussed. So with the help of local oscillator, mixer down converts the RF signal to the IF frequency band. So how this whole frequency manipulation will going to take place, we will going to discuss separately. So next is your intermediate frequency amplifier. As the name suggests, it will only going to amplify those frequency component which would have been translated over the IF frequencies. So it basically having your high gain. It will basically going to amplify the intermediate frequency signal with high gain significantly up to 10 to the power 6. So here the gain value is quite high. It further going to reject the adjacent channel or nearby frequency signals and suppress the interference, which is basically the measure of your high frequency selectivity. That is, it will only going to amplify those frequency component which are lying into that intermediate frequency ranges. So its bandwidth is same as that of signal bandwidth. Here we shouldn't want any unwanted frequency component, so its bandwidth is same as your signal bandwidth. So it will only going to provide the amplification operation over our massive signal bandwidth only. Then we will be having this detector or demodulator. So depending upon our application, we will be having different variety of detectors or applications, such as if you are using your AM signal, then we will be having this AM detector. If it has been used in your FM application, then any of the FM demodulator will going to serve the purpose. If it is TV, then we will be having TV detector, etc. So since we are only being focused about your AM application, so here your detector is your typical envelope detector. So which will basically use to demodulate or recovers the message signal. Next is your automatic gain control. The application of automatic gain control we have already discussed. So the AGC helps to maintain the constant output voltage level over a wide range of varied RF input signal levels. One more important point is there, that is the received signal from the tuned station is constantly changing as the result of changing weather and atmospheric condition. Since channel conditions are quite dynamic and due to the movement of user also, we will be having constantly changing signal reception quality. So it basically tries to nullify that effect and provides the user much better signal quality reception. So AGC allows you to listen to the station without constantly monitoring the volume control. So it is the major advantage of this automatic gain control. Otherwise, suppose if you are trying to listen certain music or channel while moving, then you have to use your volume control knob multiple times depending upon your movement. So automatic gain control basically limits that particular problem. So next is your local oscillator. So here we will specifically discuss about the local oscillator frequency operation. So local oscillator allows tuning to the receiver to a desired frequency channel. That is, it will basically going to give the input to your RF amplifier that which particular frequency band it must have to select. So it has ganked with your RF section and the mixer. As we have already discussed, that is your RF section and mixer both will going to have same frequency input so that they can function in the synchronous fashion. So FLO will be equal to FC plus F of IF, where FLO is basically representing your local oscillator frequency and that will be equal to the summation of your carrier frequency as well as your intermediate frequency or standard intermediate frequency, which is in case of your AM that will be equal to 455 kilohertz. So intermediate frequency must be such that the image response is rejected by the amplifier. So if you talk about your upside conversion, that turns out to be your FC plus IF, and if you talk about your downside conversion, then local oscillator frequency will be equal to FC minus F of IF. So any of the local carrier oscillator frequency can be used. They will going to produce the same intermediate frequency outcome. But here in this heterodyne receiver, we will be using this upside conversion, that is your FC plus IF. Since we are using this upside conversion, so that is why this heterodyne receiver would have been termed as or called as your super heterodyne receiver. So next point is image frequency rejection. That is how we will going to reject that image frequency. So image response, the same effect as that of the desired signal must be rejected. Otherwise, it will going to produce some interference. So image frequency, if you talk about this image frequency, so in your up conversion, the image frequency will going to have is your F of image will be equal to F of LO plus F of IF, that will be equal to FC plus 2 of IF. Whereas if we consider your downside conversion, although in your super heterodyne receiver we are using this upside conversion, but in your downside conversion, image frequency would have been evaluated as your F of LO minus F of IF. So when we're going to put this FLO as FC minus F of IF, we are left with your FC minus twice of IF. So for upside conversion, we'll be having image frequency value will be equal to FC plus 2 of IF, and for downside conversion, we'll be having this image frequency value that will be equal to FC minus twice of IF. So in both the cases, if we want to perform this image rejection, then we have to make sure the bandwidth of your message signal must be less than twice of intermediate frequency. Just because if this is not be the case, and if your message signal bandwidth is greater than this particular value, twice of IF, then in that particular case interference will going to happen, and if we want to avoid it, then that case should be validated. Let us understand this image rejection with some example. So let us say that incoming RF signal FC value will be equal to 850 kilohertz. This is your central carrier frequency, and for the standard intermediate frequency value will be equal to 455 kilohertz, obviously for your AM broadcast systems. So upside conversion, your FLO or local oscillator frequency would be given as the summation of your this FC plus IF, that will be equal to 1305 kilohertz. So as per this upside conversion, your image frequency will equal to f of LO plus f of IF, that will be equal to FC plus twice of IF, so that will be equal to 1760 kilohertz. So this basically signifying that our message signal which would have been broadcast at this central carrier frequency FC is equal to 850 kilohertz will going to have this image at 1760 kilohertz. So this particular figure is basically showing the multiple frequency component in your heterodyne receiver. Here this particular line, this is basically showing your RF response of the filter. This is basically showing the input signal in the frequency domain, and this is basically representing the intermediate filter response. So this particular portion is basically showing your message signal value that would have been centered around your FC, which will be your 850 kilohertz. So that signal bandwidth will be equal to FC plus FM and FC minus FM. So this is your actual message signal. And this particular point is basically showing your local oscillator frequency, which we have evaluated as your 1305 kilohertz over here. So that is your 1305 kilohertz. And for this upside conversion, your image frequency value turns out to be your 1760 kilohertz. So at this particular point, we will going to receive the same signal value or the image of this particular message signal. So in order to avoid that particular thing, what we could do is we have to make sure that your signal bandwidth, that is this bandwidth I am talking about, this bandwidth should always be lesser than your twice of IF, that is your 910 kilohertz. So if this will be the case, then at this particular point we will going to get the image of that particular signal, and we can easily observe that here at this particular point our filter gain is quite lower. So if this is the signal strength in comparison to this is your image response, so we can easily nullify the effect of this your image frequency. So this is how image frequency rejection will going to take place. So intermediate frequency must be high enough to reject the image response. As we can see from this particular figure, for image frequency it is better that it should be farther away from this central message signal or central carrier frequency translated message signal. So if it is as farther away from this message signal, it will be good for us, just because at this particular farther away point we will be having very low gain of our amplifier. So intermediate frequency, side by side intermediate frequency value must have to be also low, so that we can have this high gain and adjacent channel interference suppression also. So these two are your complementary points. So obviously we must have to perform a trade-off so that we can get this better response of the system. So now this particular figure is basically showing the frequency conversion process that has been happened in this whole super heterodyne receiver. So this is the block diagram structure of your super heterodyne receiver. So just try to understand them parallelly, that in which particular block which type of operation will going to take place. So here we are assuming that we'll be having this your incoming AM signal at your 99 kilohertz, 1000 kilohertz and 1001 kilohertz. So these are your message signal, and your central carrier frequency is your 1000 kilohertz. So for this FC value 1000, your local carrier oscillator frequency will turns out to be 1000 plus 455 kilohertz, that is your 1455 kilohertz. So this will be the input to your mixer. So mixer will going to get these sort of input. Your local carrier oscillator frequency is your 1455 kilohertz, and input frequency signals are your 99 kilohertz, 1000 kilohertz and 1001 kilohertz. So as we had already mentioned that mixer will going to produce the combination of different outcomes, that is it will going to produce the summation frequency components of these two, difference frequency component of these two, and individual frequency component of all those stuff. So if we will going to get the outcome of this mixer, that turns out to be 454, 455 and 456, which is nothing but it is the difference of these frequency component, that is your 1455 kilohertz minus these frequency components. So that turns out to be 454 kilohertz, 455 kilohertz, 456 kilohertz. Then next three components are those soul signals, that is the input of this mixer, that is your 999, 1000 and 1001 kilohertz. Then next is this frequency of your local oscillator frequency, that is equal to 1455 kilohertz, and this is the part where we'll be having this summation of all these frequencies, that is 1455 kilohertz plus 999, 1455 kilohertz plus 1000, 1455 plus 1001. So these are the frequency associated with your summation frequency. So mixer outcome will be these frequencies. So then next mixer output will get passed through the intermediate frequency amplifier, which is basically tuned to your 455 kilohertz intermediate frequency only. So it will only going to amplify those frequency components which are lying in this particular frequency band, that is your 455 kilohertz. So it will only going to amplify these particular portions of frequencies, and it will going to reject all other frequency components. So at the output of your intermediate frequency amplifier, we will be having this 454, 455 and 456 kilohertz, and this is basically the amplified outcome of your IF amplifier, and that particular signal will then pass through the detector circuitry, and at the detector output we will going to get our baseband signal or voice signal as an outcome. So hopefully you guys have got the idea about the frequency conversion process in your super heterodyne receiver. So now in this particular slide, we will try to give the overview of both type of receiver that we have studied, that is your TRF as well as your super heterodyne receiver. Obviously this overview will be based on their construction and principle of operation. So in your tuned radio frequency receiver, it is composed of your RF amplifier as well as detector. We have already seen that. No frequency conversion will going to take place. Obviously here we are talking about your intermediate frequency conversion. There will be no intermediate frequency conversion in your tuned radio frequency receiver, whereas this would happen in your heterodyne receiver. So it is not often used just because at high frequency operation its response is not good. That is why it is not oftenly used. It is difficult to design tunable RF stages due to the non-linearity existing in your amplifiers. Difficult to obtain high gain RF amplifiers, since at high frequency of applications gain of the amplifier will get reduced. Whereas in your super heterodyne receiver, we will going to down convert the RF signal to the lower intermediate frequency, which will going to overcome the different problems associated with your TRF receiver. So that is why in that contrast we could say that it is the best receiver available. Main amplification takes place at the intermediate frequency only. So hopefully you guys have got the insight about both types of receiver, that is your tuned radio frequency receiver as well as your super heterodyne receiver, and why super heterodyne receiver is having superior quality over your tuned radio frequency receivers. In case of any doubt, you can ask me in the comment section. I'll try to solve them out as soon as possible. So these are the references. Thank you very much for your patient hearing.